Welcome. In this video we are studying the behavior of gases when they are under what we call adiabatic conditions. They cannot exchange any heat with their environment. Now, the typical way we study gases is using something called the ideal gas law. And the equation of state for the ideal gas law is very well known. PV equals NKT, where N is the amount of gas here, in this case the number of particles that we have, P is the pressure, V is the volume, T is the temperature of our system, and K is something called Boltzmann's constant. However, this doesn't tell the whole picture for a system whenever we are at adiabatic conditions. For example, we know, right, that whenever gas expands, its temperature should drop. But if we leave pressure, number, and the constant, then if the volume got bigger, this says the temperature should get bigger. That's obviously not right, and so we're actually missing part of the story here. We're missing anything that has to do with heat, anything that has to do with thermal energy flow into the system using this equation. To recover that, what I'm going to do is I'm going to look at two different systems, both of which we can well understand the role of heat, and then I'm going to mix them together. The first system that I'm going to look at is called a closed system. In a closed system, we control the number of particles, we control the volume of the system, and the measure of energy that we have in the system is called the internal energy and is typically written with the letter U. The other system I'm going to look at is called a constant pressure system. In a constant pressure system, we control the number of particles, but we can actually move this top system up and down, and I can apply a force, a large force, onto this top system, and I can control the pressure of this system. In a constant pressure system, the measure of entropy that we will be interested in is called enthalpy, and it is typically written with the letter H. Now, for both of these systems, we will be looking at something that we call the heat capacity of these systems. The definition of heat capacity is as follows. The definition is that the heat capacity is equal to the change in energy over a change in temperature to the system. So if I bring in some external system at a different temperature and let this thing change temperature, I want to know how much energy changes in the system. That's given by the heat capacity. For both of these systems, what I want to do is look at the first law of thermodynamics and what it says about the heat capacity when I'm in an adiabatic condition, when no heat can flow in or out of the system. The first law of thermodynamics for the closed system is a little bit easier. This says that the total energy available to the system will be, or a change in energy, will be some heat that I put into the system. That's given by dQ. Q is our standard symbol for heat, then minus any work done on the system or by the system. And again, remember that we control the volume here. So if we change the volume slightly, that'll be work that'll be done by the system, and the amount of work that it will do will be pressure times the volume, where pressure is some measured quantity in our system here. For the constant pressure system, the first law of thermodynamics looks slightly different. The first part's the same. Any change in enthalpy in the system, any change in the total available energy in this constant pressure system will be due to some heat I put either into or take out of the system, or it will be due to changes in pressure within the system. And so these two are the first law of thermodynamics for a closed system and for a constant pressure system. Now I can use these because this is change in energy. Change in energy for a closed system here, change in energy for a constant pressure system here. Since the coefficient, or since the heat capacity, and this is going to be heat capacity at constant volume, this heat capacity at constant volume for a system that cannot exchange heat with its environments. So dQ is going to be 0 because I'm not exchanging heat. It will be minus P dV over some change in temperature. Similarly, the heat capacity of constant pressure for the constant pressure system will be positive V dP over dt. Now the trick that I employed here is I look at these two systems, both of which has an explicit role played by heat, so that I can get rid of those two environments. Now, here is the really neat part. We're going to do a little bit of algebra and a little bit of calculus, and we're going to take these two expressions and we're going to find out the relationship that pressure and volume have in an ideal gas when we don't have any exchange of heat with the environment. The first thing that we're going to do is we're actually going to define something that we call the adiabatic constant. The adiabatic constant is written gamma. It is the heat capacity at constant pressure divided by the heat capacity at constant volume. Now, why are we going to do that? I'm actually going to rewrite over here this adiabatic constant is equal to minus V dP over P dV. Now, as we have it here, we have this ratio of these two heat capacities, but I'm telling you that this guy right here is a constant for our system. So what I can do is I can multiply everything on the bottom over here. I can get all of the terms with V on the same side, all the terms with P on the same side, and I'm going to have a differential equation. So let me do that. Now, if I want to solve this differential equation, which has a differential or has an infinitesimal on both sides, I need to integrate it. I know what the integral of 1 over x dx is. That's the log. I have to integrate it from some initial value to some final value, so that's going to be the log of the ratios of those. And now comes something that we can take advantage of, which is the behavior of logarithms with multiplication to exponentiation. So I can take this gamma and I can raise my volumes to that exponent. I can take this minus sign, it's minus 1, and I can raise my system to those. Now I have two simple logs. I can just get rid of the logs. It'd be the equivalent to exponentiating both sides. So I'm just going to get rid of the logs here. Now I have this relationship. The final thing that I'm going to do is I'm simply going to rewrite this side, which has the final on top and the initial on bottom. Since this is simply to the -1 power, I can flip it over. So I'm going to rewrite that. And now I've got where I want to go. This system, as we have here, gives a relationship of how changes in volumes relate to changes in pressure. But more than that, if I take and I multiply both sides by PF, by the final pressure, and I multiply both sides by V naught to the gamma, by the initial volume to the gammath power, then what I get is the following. I get something that on the one side only depends on the final values, and on the other side only depends on the initial values. This tells me that this product has to be a constant for the system at constant entropy, or at constant, there is that word that I was dancing around. For a system that doesn't exchange any heat with its environment, this ratio, PV to the gamma, has to remain constant for the system. Now, I can actually use that and the ideal gas law to get some more stuff, some more relationships for our system. So I'm going to erase some of this and do that. First, let's look at, let's rewrite the ideal gas law, which is PV is equal to NKT. And now let's multiply both sides of the ideal gas law by V to the gamma minus 1 power. Why gamma minus 1? Because when I multiply V times V to the gamma minus 1, I add the exponents, V to the 1, V to the gamma minus 1, the 1 and minus 1 cancel. And on one side, I'm going to get PV to the gamma. On the other side, I'm going to get NKTV to the gamma minus 1. Now, at this point, I should realize this expression here, PV to the gamma, is a constant, But so is n, the number of particles in our system. We're not losing or gaining particles. And so is k. It's a physical constant. So I'm going to move those to the other side. And now I have the relationship that everything on this side is constant, so this side has to be constant as well. So I get my new relationship, which is T v to the gamma minus 1 is equal to a constant. But just like last time, if these things are equal to a constant, I can also write this in terms of relationship, in terms of a ratio. And so this would say T final over T initial is equal to V initial over V final to the gamma minus 1 power. Wonderful. Now, how do we get a relationship? So we have a relationship now between T and volume, between pressure and volume. How do I get a relationship between temperature and pressure? Now, in order to look at the next system, I'm going to have to do something that's a little more subtle. Start with the ideal gas law again. PV equals NKT. Now I'm going to multiply both sides by P to the 1 over gamma minus 1. Again, on one side, I'm going to P to the 1 over gamma. V is equal to NK TP to the 1 over gamma minus 1. But this right here can be rewritten. I can factor out a gammath power. P V to the gamma, the 1 over gamma, is going to be equal, I'm going to divide both sides by NK. T P to the 1 over gamma minus 1. Now we know that this is a constant. A constant to a power is still a constant. N and K are constants. So our next relationship is T P 1 over gamma minus 1 is also equal to a different constant. And again, we can do this same thing with ratios. I can rewrite this. T final over T initial is equal to P initial over P final to the 1 over gamma minus 1. And so these are the relationships that we will use whenever we talk about how a gas behaves in an adiabatic system, in a system where it cannot exchange energy with its environment.